Hi there, everyone. So now we're going to do our first video for the Lab 1. I'm going to share my screen. So let's go into Lab 1. So we open Lab 1. So you can kind of see at the onset, each of the labs has certain number of activities, like Lab 1 has 12 activities. So you already know you're looking to do about 12 things there, and then that's what you're going to be reporting on your that's what you're going to present in your Lab 1. So as you proceed through this, the lab actually grades it for you, and even if you take the Lab 1 quiz, it grades it for you, and it gives you a total score. And I can actually see your total scores, but I don't grade you based on those total scores. I grade you based on what you submit in a PDF file, and you upload it to the Canvas page. This one will be due by Friday night. So just remember that you can upload it up to Friday midnight. If you upload it earlier and I somehow grade it, once I grade it, then you cannot make changes to it. So if you upload it and you later on you think that you maybe made a mistake or you left something out, if I haven't graded it yet, then you can always resubmit, right? But once I have given you a grade, then you cannot resubmit. So just be careful on uploading it quickly. Make sure you got everything complete, But in terms of what the score the lab gives you, don't worry about that. That's not going to depend. That's going to change. That's not going to change your grade. So you got 12 activities here. So let's start with measurement. And within the 4 activities that are lined here, there is sub-activities. So in total, they add to 12 activities. So I'll walk you through some of these and show you what you need to do. So you could just hit the next button here. So at first, it gives you a little bit about measurements and units. And then you can read that. Length units. Okay, so it gives you a little bit about distance units measured in astronomy, particularly, like the parsec unit, which is equal to 3.26 light years, and then the light year unit, which is 63,000 AUs, and the AU unit, which is the distance between the Earth and the Sun. So in terms of kilometers. So then it also gives you the conversion between the meter and the feet. 1 meter is 3.281 feet. And then it tells you what the centimeter, the millimeter, the nanometer, and the angstrom, the conversions for that. So the very first exercise, you can just click it right here. Oh, okay, so this is a simple one. It's saying use the mouse to drag the unit boxes into the correct order from largest on the left to smallest on the right. So I'll show you for this particular one how to do it, but I'm not going to show you every single time what to do, but I'm just giving you this as an example. So for this one, from largest to smallest, the parsec is going to be the largest. You put that here. The light year is going to come next. You put that there. The AU is going to come next. And then the kilometer. And then the meter. And then once you click submit answer, and then you could take a snapshot of that. So that's your snapshot right there, showing the answer in the order that you have and showing that you got all correct. So that'll be your first snapshot. Then you can call that length unit exercise, Lab 1 length unit exercise. And then you can keep proceeding. Like I said, you can write that in hand or you could type it, a length unit exercise, and then you can submit this picture under that heading. And then click next. And then you go next. Okay, so I guess you just click, well, submit grading for activity. And then you just go to the next arrow. And then it gives you a conversion, how to do a conversion here, nickels in dollars. So it says, let's say you're trying to convert $25 into nickels. So then you use the fact that $1 is 4 quarters, and then 1 quarter is 5 nickels. And then you multiply 25 times 4, 100 times 5. So $25 will be equal to 500 nickels. So you always put on the bottom of the fraction the unit that you want to cancel. So this can cancel with that. And then you put the quarter here on the bottom so that this will cancel with that. Okay, so then comes the next exercise. Here, this one. It's like a measurement exercise. Click on the ruler and drag it to move to a new location. Press the shift key and then click on the ruler and drag to make the ruler rotate. So you're trying to measure the distance between here and here using a given ruler. So you could put this at the edge and then press shift, rotate it, and then zoom in on it. I'm doing control plus to zoom in. So put this at the middle of the dot. So that's 10 full centimeters. So that would be one snapshot you can do right there. A snapshot of that for this second portion. And then wherever this ruler left off, then move this over wherever you left off. So that was already 10 centimeters, right? Then you move this to the edge of that, and then you measure to the center. So that looks like about 2.4 centimeters, 2.4, something like that, yeah. So if I did the moving correctly, then you add the 10 plus the 2.4, and then you, that'll be 12.4 centimeters. So then you take 2 snapshots of that. One was like that, and then one moving it to the edge like that. Right there. I might have moved it wrong. Yeah, something like this. Yeah, it would be a little bit less than 2 actually. So then that'd be 2 snapshots. But with that one, I don't think there is any calculation you're doing. Yeah, no calculation. You're just presenting that data and the pictures. Okay, next, unit 1 conversion exercise. So Cepheid variable. So Cepheid variable star is a variable star which varies in brightness. We also say that it pulsates. These are stars that are dying, and when they're in their death process, they periodically brighten and dim. So we're going to try to figure out how long this Cepheid variable star takes to brighten and dim. So then we press play. You see how it's brightening, dimming, brighten, dim, bright, dim. So every time the brightness is going up, it's getting bright. Every time this thing is going down, it's getting dimmer. So I can stop this at any point. And what it's telling us here is that 1 centimeter of this scale, it's already giving us the scale. It's telling us that that represents 5 days, the graph scale. So 1 centimeter from here to here represents 5 days. So we want to know how many days it takes from one bright to the next bright, or from the one dim to the next dim. But the problem with the dim part is that the trough is kind of more wider. It's hard to tell where the middle of that is. So I'm going to focus on the top one, the brightest part, because it's a sharper peak. So then I'm going to take this ruler, go over there, now zoom in on it. Control plus, zooms in. So then zoom in, you see there, And I want to measure how many days, how many centimeters from one peak to peak. So about, it looks like it's about 2.35 centimeters. You see 2.35, maybe if I zoom in more. Ah, that's really nice right there. So it's, this one is 2.3. Actually, let me move this edge right where the peak is. No, you know what? It's 2.3 right there. 2.3. So if I start the ruler right where that peak edge is right there, then this one is going to be 2.3 centimeters, right? So then you would have that snapshot, take a snapshot of that ruler, and then he put here 2.3 centimeters, and then they're already telling you that 1 centimeter is 5 days, and then you make the calculation how many days it takes for this Cepheid variable to go from one bright to the next bright, you see. So so that'd be your, I believe that's the third activity that we've done, right? One with the ruler, one with the previous one, and one with this. So that's 3. And now this is the next one, lab 1 unit conversion exercise 2. So this is going to be the 4th activity. So then we go down here. Okay, so they've already given us the curve. They want us to decide, you know what, let me zoom out. They want us to decide, oh, this is the number of sunspots. So that one of the things we learn in astronomy lecture is that the sunspots go through a cycle, periodic cycle of high number of sunspots, low number of sunspots. So they say it takes about 11 years in the lecture portion of the class. Well, let's prove that. Let's see if it is 11. So the first thing we have to do on this one is we have to actually make our scale, right? So they're telling us from here to here is a 50-year span. So to make the scale, 1 centimeter is how many years? I have to first put this here and make our scale. See, on the previous one, they gave us the scale. So I have to do this like this. Okay. And then I have to say, let's say I zoom in. Where was my ruler? Oops. Did it disappear? Oh, it was all the way to the right. Okay. When I'm zooming in. Oh, there it is. Okay. Yeah. So when you zoom in, it goes off the page. So now you go like this. So it looks like 2.5 centimeters is equivalent to 50 years, right? So then you take a snapshot of that. 2.5 centimeters is equal to 50 years. So then what would 1 centimeter equal, right? So then you can show the work for that. If 2.5 centimeters is 50 years, what would 1 centimeter be? Then you can divide 50 divided by 2.5, 20. Oh, okay. So you see, so that means 1 centimeter of distance is equal to 20 years. Okay. So now let's go to back to there. Where was I? Okay. Now let's do zoom out. So now I go to my graph. So on that one, I need a couple snapshots, right? One of the scale itself. Okay, now I need to put the ruler next to, let's see here. You know what? Let me control plus, 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 plus. Oh, the ruler went all the way up. Let's see here. Oh, there you have it. Maybe on this one you need to zoom kind of more. Oh, there you go. So you could kind of say, okay, what's the distance? So let's say from the middle of the A, right there, all the way to the B. That looks like 0.5, right? From here to here, it looks like 0.5. It does look like a little bit less than 0.5 if you look at it. You see here? Kind of right there. This one right here, the peak of this, it looks like 0.48 centimeters. You know, it's a tad bit to the left of 0.5. Right there. That's a great snapshot you can take right there. 0.48 centimeters. So then if the distance between two peaks of sunspots is 0.48 centimeters, what was my scale? 1 centimeter was 20 years, right? So what's 0.48? 0.48 times 20. 9.6 years. So that means the sunspot cycle happens every 9.6 years. Right? So it's supposed to be what? What's the answer supposed to be? Let's look it up here. Sunspot cycle. The sunspot cycle is supposed to be a 11-year cycle, usually, you know, so it's not exactly 11, and it might vary slightly from century to century. So it's an 11-year cycle, they're saying. So what would be our, let's just say that it is exactly 11 years. So what would be our error? So we can now compute. For that one, I want you to also compute percent error, even though the lab manual, the lab doesn't ask us to do percent error. So once you get your result, then how would I calculate the percent error? So we'll go to the whiteboard. So 100% times, we take the absolute value of what I got, or since, yeah, the order that we subtracted doesn't matter since we're taking absolute value. So we do 9.6 is the number that I got, minus 11 is what I'm supposed to get, divided by what I'm supposed to get. Okay, so let's see what that is. It's not that good. let's see here. So 11 minus 9.6. So 11 minus 9.6 is 1.4. So you first subtract this. You're taking the absolute value of negative 1.4, right? So it's just going to give you 1.4. And then you divide it by 100. Divide that by 100, which you get 0.014. Then you multiply it by 100. By 100 to convert to a percentage. So 1.4% error. Actually, it's decent. I would have liked a little bit closer, but remember that this 11-year cycle is not exact and it could vary. So within the unexactness of the 11-year cycle, we are close. So that's what you would report as your percent error for that activity. And then you would include for that activity, you would include, let's go back to sharing the screen. Desktop. Okay, so now let's go to, where were we? Right there. Okay, so now let's zoom out. Where are we now? So we did this one. We did this one. And now we're gonna do this one. So the graph above shows the number of sunspots as a function of time along with the time scale. Using the ruler, determine first the conversion factor for centimeters to years on the graph, and then use that conversion factor to determine the period of this variation by measuring the interval between peaks A and B. So it's actually just seeing if you did it right, essentially. It's essentially just building up on that unit conversion exercise 2, and then you're doing this exercise. So 1 centimeter was 20 years, we said. And then the sunspot period was 9.6 years. Submit answer. Okay, so it accepted it. So then that would be another snapshot we can do for that one. So right there. This is unit conversion exercise 3. Okay, so then you take a snapshot of that. So now let's go to the next one. Where's the next one here? Submit activity. There should be an arrow here, no? I'm not sure why it's not giving us the arrow, or maybe it's control auto negative. No? Yeah, it didn't give us the arrow. Well, let's just go back to the beginning. And I believe I was on this one here. Where are we on this one? Unit 1, unit conversion exercise 3. So unit conversion exercise 3, we're on that one. So we're done with that one. Yeah, exercise 3, we are done with that one. So we can now go to, the other way to do is, no, I think it takes you back. I think the best way to do it is just to have your other is just to have this open. And then once you're done with that, then you can go like that and then go to the next unit. Scientific notation. Yeah, then you just open up, it opens up another browser. So scientific notation. So it talks about a little bit about writing big numbers. So instead of having to write 3 billion, you can write 3 times 10 to the 9th. Or 3 e to the 9th. So this 3 e to the 9th is the same thing as writing 3 times 10 to the 9th. So for big numbers. In astronomy, you have a lot of things that are full of big numbers. So conversions. So it says the exponent tells you how many places you have to move the decimal if you want to write the number in decimal. For example, 5.51 times 10 to the 4th is 5.51 e to the 4th. Means move the decimal point 4 places to the right. So if you move 4 places to the right, it's going to be equivalent to 55,100. 5.51 times 10 to the minus 4 means move the decimal point 4 places to the left, giving you 0.0051. If the exponent is 0, the decimal point does not move. So 3 times 10 to the power 0 equals 3. So note that the number written without a decimal point has an implicit decimal point to the right of its last digit. For example, 3 implies 3.0 in scientific notation. So this is the next one then. So scientific notation conversion example. So 6.0. Yeah, but this is not an exercise. So this is not something you would submit. You're just sort of watching them do it. Yeah, they're showing you examples essentially. So this one, go back, and I think that's it for that. Okay, now this is the next exercise. Okay, so question 1, write the answer in decimal, write this answer in decimal notation, right? So you would just write that in, let's say 3, 5, 4, right? I believe it's just gonna be 3, 5, 4, how many zeros? Let's see here. 6 zeros, right? 1, 2, 3, 4, 5, 6. Correct. I think for this one, we could just take a snapshot way at the end. So question 2, question 3, let's just say I didn't attempt any of these. And then at the end, when I submit, that way you don't have to take a snapshot on every single one, you know. You could just take a snapshot for your whole score. So scientific notation exercise, submit for grading. So, okay, so basically that would have been the snapshot that you took, the one that I just showed you in the previous page, where you only show your total score. Because there's too many of them, that one, it's better just to take one overall one, just to show your grade. Okay, now we don't need to restart this. So I think that's it for that one. See, so when you don't see any more arrow, that means you're done with that unit. So let's exit out of that. Go back to that one. Okay, so now we're done with that one and that one. Now we go to I believe that's the last one, angular measurements. So try to do your best on that scientific notation one. I think it allows you to take it once or twice. So try to do your best. But your score on that one necessarily is not going to determine your score on the lab. But if I notice that you did 0 out of 10, that means you just skipped all of them. You didn't do anything. So try to do a good score, of course. But just because you got 8 out of 10 doesn't mean that your score on the lab will be 8 out of 10. So try to give it a good faith try, essentially. So now the last part, apparent distance in the sky. So then you have here degrees, arc minutes, and arc seconds. So this animation shows relationship between degree, arc minutes, and arc seconds. So 1 degree is 1/360th of a circle. And I press play. Then we can take a degree and split it up into 60 equal parts, and that would be an arc minute. So it's such a very small sliver of an angle, an arc minute. It's 1/60th of 1 degree. And 1 degree is 1/360th of a circle. Then we can even take an arc minute and split it up into 60 equal parts, called an arc second. You see? So that's such a very, very small sliver of an angle. So now it says here, angular unit chart, 1 degree is 1/360th of a circle as denoted by 1 degree. 1 arc minute is 1/60th of a degree as denoted by 1. And the way to write arc minute is like this one, the 1 slash. And then the 1 arc second is 1/60th of an arc minute as 2 slashes like this. So it's kind of how we write actually minutes and seconds. If something took 2 minutes, you could actually write it like this, 2 with slash 2 minutes. And then if it's something to 2 seconds, then you could write 2 seconds like that. So it's very similar to how we count time. Okay, so then we do the arrow. So angular size. If we know the angular size of an object and we know how far away it is, we can figure out the linear size of that. So that's how angular size is used. The angular size is A. In other words, it's how big that object appears in the sky. That's what angular size is. And the distance to that object is R. And then S is the diameter of that object, you see? S is the diameter. So it says, as mentioned earlier, angular measurements are often used to determine sizes that cannot be measured directly. So we can determine the size of the moon as long as we had a technique to determine the distance to the moon. We can determine the size of the moon if we knew the angular diameter of the moon, you see? Okay, then we go to the next one. Radians. We must convert the angle into radians before we can relate the distance to linear size. So before computation, the angle A must be converted into radians. The radian is angle associated with arc that comes from wrapping one circle radius around the outside of the circle. So let's see what a radian is. Oh, okay. So basically, definition of a radian is this. If you take the radius of a circle, and let's say it was a rubbery radius that you can bend along like this. So if this distance and this distance is the same, right? No matter what, let's say this is 1 meter and this is 1 meter, or this is 2 meters and this is 2 meters. So it doesn't matter what that is. Then the angle subtended by that arc is 1 radian. That's the official definition of the radian. The radian is a certain angle where the distance along the arc is equal to the radius, right? So let's see here. So this is now 2 radians, 3 radians, and then 0.14. So in a circle, you have in a half of a circle, you have pi radians, right? 3.14. So you can get 3 perfect radians and then plus a pi. That's why the circumference of the circle is pi, 2 pi r times the radius, right? So there's that extra 0.14. Okay, so let's see here. So using angle measurements to compute lengths are useful, especially when the distances are extremely large. For example, the earlier equation SSRA can be used to compute the diameter of the moon. The moon takes up about half a degree of an arc in the sky. So we can say the angular diameter, the angular size of the moon is about a half a degree in the sky, half of a degree. And now you need to have already measured the distance to the moon with another technique. So they're already giving us the distance to the moon from the Earth is 384. Then we can now find the size of the moon. The diameter S can be found by multiplying R and A. So you just take the S is the R, which is the distance to the moon, multiplying it by A. But the first thing that they're doing, they're converting the angle A to units of radians, right? So since the angle was given in units of degrees here, we have to convert that to radians first. So to convert, we say half a degree, and we put 57.3 degrees is 1 radian. Now, I'd rather you do it this way, because this kind of confused things. Where did they get the 57 degrees from? So I'd rather you do it this way. Let me share the whiteboard. So you could do it this way, 0.5 degrees, and then use the fact that 180 degrees is pi radians. And that gives you better, more accurate result. The rate that they got 57.3 is they divided 180 by 3.14. That's how they got 57.3. But this is more exact. Remember how we saw that in the animation that 180 degrees has 3.14 radians. So this is exact. This is very exact. So on your calculator, you would say, let's go to the calculator now. So you would say 0.5 times pi divided by 180. Let's see. So leave pi as pi so that it actually is more than 3.14. It's slightly larger. So then that gives you 0.0087. So we could go to the, so that's going to be the angle, 0.0087 to, let's go to 4 decimals here, 0.008727. So then our answer will be so that's the angle, 0.008727 rads. That's probably going to be more accurate than the result that they had. Okay. So then let's go back to the lab that they did, the example that they did. Okay. Oh, you see here how they have 0.0087. So it's 0.008727 radians. So then plug in the value for the equation S is our times A. So do you take the distance to the moon, right? And then you multiply that by the angle as measured in radians, right? And then that gives you the diameter of the moon. Let's see how accurate that is. What is the diameter of the moon? Diameter of moon. That's written in kilometers. I mean, that's written in miles. Oh, right here. Okay, the diameter is about 3,475 kilometers. 3,475. Is that close? Not that close. Well, that's because this angle that they're giving us, this the moon takes up about 0.5 degrees. They're giving us a rounded number. It doesn't actually take exactly 0.5 degrees of arc. It's probably slightly bigger than 0.5. And it also depends if the moon is close to us or far from us. So because its path around the Earth is elliptical. So even this angle slightly changes depending on its distance from us. So this is not meant to be an exact example, you know. But it's in the ballpark. So now the results in the lunar diameter is S. Okay, so using S is our A. Convert the maximum angular diameter for each planet from arc seconds into radians using the provided calculator. Oh, is that a calculator? Calculator. You can select the planet using the drop-down menu. Type the value in arc seconds and then press the button convert to obtain the corresponding value in radians. When you type a value for R or S, the second value will be calculated automatically. Oh, okay. So this is another one of the exercises here. So let's say they're telling you that let's see here, for Jupiter, convert the maximum angular diameter. Okay. You know what? We couldn't do anything here because it didn't give us the angular diameter. There was nothing. Okay, so yeah, we couldn't do anything here basically because there was nothing provided. So you have to actually go and start the exercise in order for you to do this. Oh, okay, there you go. So now we have Jupiter is the arcs. It's telling us that its angular diameter is 50.4 arc seconds. Okay, so then we have to convert that to radians. Right? So this example is meant to be a little bit more exact, I think, because they're giving you the angular arc seconds down to 1 decimal place. So if we have the arc seconds here, so then you put 50, Jupiter, 50.4 arc seconds. Oh, okay. So then this is a calculator that's converting it for us to radians. You see? So it's already converting the it's already converting what you did here into radians. So then you would just put here the answer. So we would say 2.443 e to the minus 4. 2.443 times, nope, times 10 to the power negative 4. You see? So I'm using that calculator thing that it did. You see? So now for this one, they're choosing to give us the diameter of Jupiter. So they're asking us to calculate the R, right? So in your so then we can do the work. How would we get this? If I want to get the R of the so basically it's S equals R theta, right? So let's go to the yeah, whiteboard. Let's clear this. Okay, so now we have S is R theta. So I'm going to get the results that they're giving us here. So S is equal to 1.39822. 1.39822. 1.39822 is the S times 10 to the 5th. Yeah. So then the radians that we got was 2.443 times 10 to the 4th. 2.443 times 10 to the 4th. 10 to the minus 4. 2.443 times 10 to the minus 4. Right? That's when we did the conversion from arc seconds to radians. So this was what the calculator gave us. So then the S, the table is giving us. But remember, it's times 10 to the 5th kilometers. So this is times 10 to the 5th kilometers. Okay, so then how do we get the R? We take this number and then we divide it by this number. So I'll show you how to do that on the calculator now. 1.39822 times 10 to the 5th is equal to R divided by that number. So now we have here, go to the calculator. 1.39, or let's just put it on parentheses, 1.39822 times 10 to the power 5 divided by, okay, and then the radians that we got was what? 2.443 times 10 to the minus 4. 2.443 times 10 to the power negative 4. Okay, that's going to be the distance to Jupiter, right? So the R. So let's write this in scientific notation. So how many times back do we have to go? 1, 2, 3, 4, 5, 6, 7, 8. So we can write 5.723, maybe go that many spaces. So 5.723, 1, 2, 3, 4, 5, 6, 7, 8. 5.723. Right? So then we'll have here 5.723, right, times 10 to the power 8 kilometers. Well, we don't need to put the units, yeah, because the units are already up here. You see? So that would be the, and I'm kind of using in terms of sig figs, since this has 4 sig figs and then this has 4 sig figs. This has more sig figs, but I'm just going with the less of the 2 sig figs. You know, so that's enough of an accuracy. So the Saturn, they've already filled it for us, huh? Everything about Saturn. It seems like that was already filled. So then I'm doing the stuff for Uranus. So then I'm converting the 3.6. Well, let's check for a second if the Jupiters came out okay. What's the distance to Jupiter? So distance to Jupiter in kilometers. Keeps giving it to us in miles. Or the other way to look at it is always just through Wikipedia. Let's say usually Wikipedia will have all the information you need on any planet or a star. On the right side over here. Yeah, it has the distance to Jupiter in, it has it in AUs, semi-major axis, 5.2 AU. Gigameters, 778.57. This means 778.57 gigameters. So are we close there? 778.57 gigameters. There, that's the way that they're writing it, 778.57 gigameters. So online, it's saying 778.57 gigameters. 778.57 giga means 10 to the 9th, right? 10 to the 9th meters. What was the result we got when we did it on the calculator? We got 5.723 times 10 to the 8 meters, right? No, 5.723 times 10 to the 8 kilometers. So the distance that we got for the R was 5.723 times 10 to the 8 kilometers. Is that way different? How can we compare these two? Well, remember the Wikipedia was giving it to us in meters. So how can we convert that to kilometers? Well, I can say 1,000 meters is 1 kilometer. Remember back to that conversion stuff. Meter cancel. So then if you divide 10 to the 9th by 1,000, you're going to get 10 to the 6th. You're going to get 10 to the 6th, right? Times 10 to the 6th kilometers. You see, so I'm taking the Wikipedia data and trying to compare it to the result that I got for the distance r. So 778.57 times 10 to the 6 kilometers. Now, how could I make this so that it's 10 to the 8th? Well, what we can say is, if I want to compare them, I could go back 2 spaces here and then write it in scientific notation. So I'll write this 7.7857 times 10 to the 8 kilometers. In other words, this is telling me to take the decimal and to take it 6 spaces to the right, this 10 to the 6th. So what I'm saying is I'm going to go to the left. I'm going to go opposite direction to write it in scientific notation, but then I'm going to make up for going to the left by adding 2 more. So now it's saying start here and go 8 spaces to the right. Well, this number and this number is the same. If you start here and go 6 spaces to the right, it's the same as starting here and going 8 spaces to the right. So this is the answer that we have from the Wikipedia. So we're not that close, but we are in the same power of the 10. Okay, so for if we wanted to calculate percent error, what would that be? So then I would take the real number, 7.7857, subtract my number, and then divide it by the actual number. And I don't need the power of the 10 in the error, because as long as they're the same power of the 10, that will cancel when I do the percent error. So it's just subtract divided by that. So so then let's go to the calculator. Oh, let's make sure I get the numbers from here. Okay, so then I'm going to do 7.7857 minus 5.723 divided by 7.7857 times 100. So I can say my error is 26.5%. It's kind of high, 26.5%. So remember, I'm using don't use the aphelion or the perihelion, because aphelion is when Jupiter is farthest from the sun. Perihelion is when Jupiter is close to the sun. So the semi-major axis is the average of these two. So use that one. So I am using the correct one. 778, right? But it's not matching the result that we're getting. And that's probably most likely due to the fact that the, let's see, where were we here? Yeah, that's probably most likely due to the fact that the arc seconds they're giving us here exactly is maybe a rounded number or something, so not exact. Okay, so now we don't have to do Saturn, then we can go to Uranus. So we would take the 3.6, put it into here, 3.6, convert. Oh, no, for Uranus, or 3.6. Okay, so now we've got the radians here, 1.745 e to the minus 5. Right there. So the angular diameter of Uranus should be smaller. It should look smaller in the sky. You see, as you're going from Jupiter to Saturn, the angular diameter is decreasing, right? Because this is 10 to the minus 5 power, whereas that's 10 to the minus 4 power. So that means this planet is looking smaller than that planet. Uranus is looking smaller than Saturn, and Neptune is looking even smaller than Uranus. So this number is going to be 1.745 times e to the minus 5. 1.745 times 10 to the minus 5. Okay, then I'm going to calculate r again. Okay, the distance to that the planet, right? So they're giving us the diameter, and we're going to calculate the distance. And then same thing for Neptune. You're going to get this, and you're going to get that, and you're going to get that. Okay, so what I want you to do is basically, like they said, do all three of these, put these values in there, right? And then that will tell you what these values are. And then you can calculate the distance to that planet here. Okay, now for one of these rows, either Neptune, Uranus, or Jupiter, either Jupiter, Uranus, or Neptune, show your work. In other words, show how they're getting the radiance from this, show how they're doing the conversion, and how you are getting the R, just like I showed in the whiteboard, right? So you don't have to show your work for all three of them, Jupiter, Uranus, and Neptune. So let's say you chose Neptune to show your work. You would show how to convert 3.6 arc seconds to radians, right? And then you should get the same number as this. So you would convert that. Then you would show how to get this number. And then for the row that you chose to show the work for, also calculate the percent error. In other words, go to Wikipedia, get the distance to that planet, and also calculate the error of yours from the actual. You see? So the one that you are showing work for, either Uranus, Neptune, or Jupiter, show how you're getting the radians, how you're getting the distance, and then also calculate error. For the other ones, you don't have to calculate the error. After you're done, click submit, and then this is what you would show. You know, of course, you would show this is correct, this is correct, this is correct. And if I had put all of these in, it would show these are correct. You see, of course, it doesn't have an error column, but that's an extra. I'm asking you to calculate the error. So then take a snapshot of that. I believe that ends the lab. So on this one, there's actually just one snapshot to take. Yeah, that's it. Just one snapshot to take. just a snapshot of these numbers. And then once you submit, say partial, you know, and then it should say correct. And then that's it, I think. You don't need the picture of this one. The previous one is good enough. And I think that ends it. After that, there is no other section for this. Yeah, that's it. That was the last. Angular measurements was the last one. Okay, so there's quite a bit of work there for you to do, show work. And then again, like I said, you could type the work or handwrite it neatly and then post your pictures along with the snapshots of your scores on those, how many correct you have and all that. Okay, have a great lab 1, and then I'll post lab 2 later this week around Tuesday night or Wednesday. Okay, bye-bye.